Welcome to Part 2 of Lecture 3 for Chemistry 418 Radiochemistry. This is the second part of the lecture on radioactive decay kinetics. Lecture 3 Part 2 uses the same reading as the other part of Lecture 3, Modern Nuclear Chemistry, Chapter 3 and Chapter 17.7, and Nuclear and Radiochemistry, Chapters 4 and 5. This lecture, Part 2, is going to cover equations. We're going to look at mixtures, equilibrium, and branching. We're also going to introduce equations that can be used to calculate parent-progeny relationships and parent-multiple progeny decay chains. At the end of Part 1 of this lecture, we went over some equations. Some of those examples included the decay of a single isotope. Now we're going to start this lecture talking about the decay of a mixture of isotopes. So let's talk about a composite decay where we have two unrelated isotopes. So the sum of all the decays are just thought of as the mixture of the two isotopes. So the two isotopes are acting independently. So the two radioactive species are mixed together. We can count the total activity as a function of time. Here's an example of what a curve might look like. And you can see that it's composed of two isotopes. So we can say that activity at any given time t is just equal to the activity of isotope 1 and the activity of isotope 2. That's equal to the decay constant of 1 times the number of atoms of 1 plus the decay constant of 2 times the number of atoms of 2. We can rearrange this equation where we have the activity at any time t is equal to the activity initial of isotope 1 times e to the minus lambda t, where lambda is the lambda for isotope 1, plus the initial activity of isotope 2 times e to the minus lambda 2 times t. We can take this equation and then solve this line for this equation. So we take this equation, put it into a solving program, generate the equation of the line, which is shown here. And then we also determine the terms of the components of this equation. So t is the x-axis. So we'll be able to solve for A1 naught, A2 naught, and lambda 1 and lambda 2. We run the equation. In this case, we solve for lambda 1 and lambda 2. These values are shown here. So the lambda is provided. We can get the half-life. We can get the initial activity of isotope 2, and then the decay constant for isotope 1, the half-life of isotope 1, and the initial activity of isotope 1. We can also solve this graphically if we examine two parts. This is the longer-lived isotope. At the longer times, its decay dominates. You linearize on this semi-log figure. The longer-lived terms go back to the origin. You get around 2,000. So if I look at the value, 2,000 minus the total value would be equal to the shorter-lived isotope. So you could solve this graphically, or more directly, you can solve it by just solving for the equation of the line that was generated. Now we can expand these equations into related decays, in other words, a parent and progeny, daughter decay. So we know that we have conditions where one isotope decays into the other, the decay series being the most common examples. So here's a figure that shows the uranium-238 decay chain, also the 232 thorium, and then there's uranium-235 decay series. Those are the natural occurring decay series. However, you can pick out a number of isotopes that will often, particularly if they're far from the line of stability, they will also have decay chains. Example here, uranium-238 decays to thorium, eventually makes its way all the way down to stable lead-206. There are actually 4 series. One of them would start with neptunium-237, which is short enough lived compared to the lifetime of Earth and the solar system that it will have all decayed away. So for any system like this, for a parent progeny decay, the rate of progeny formation is dependent upon the parent decay rate minus the progeny decay rate. And it's this relationship that we're going to really exploit to help understand the equations and how we can address under relationships between parent and progeny decays. Let's consider the case of a progeny isotope being produced from the decay of a parent isotope. So we have an isotope 1 and it decays into isotope 2. So the change of isotope 2 over a function of time is just equal to the decay of the parent producing a progeny isotope and then any subsequent decay of that progeny isotope. We rearrange this equation. We get this term, we get this equation. So let's solve and substitute for N1 using N1 at times t is equal to N1 naught initial e to the minus lambda t. That equation then becomes what is seen here. Let's take a linear first order differential equation. Let's just solve by integrating the factors to solve this linear first order differential. Let's multiply by e to the minus lambda 2t. The equation then becomes what we see here, where we get the change of n2 e to the lambda 2t is equal to lambda 1, the initial amount of isotope 1 e to the lambda 2 minus lambda 1 t with respect to time. So we've gone through the equations. We now have this equation, which we further treat to reach our final equation. Now let's integrate over time. So let's provide the integral, and we get this term. So let's integrate over what we see here, lambda 1 n 1 naught e to the minus lambda 2 minus lambda 1 times t divided by the difference between lambda 2 and lambda 1. From 0 to t, the equation becomes n2 e to the lambda 2 times t minus n2 initial is equal to a ratio of the decay constant for 1 divided by the difference between the decay constant for 2 minus 1 times this term n1 e to the lambda 2 minus lambda 1 times t minus 1. Multiply by e to the minus lambda 2 times t and solve for n2. Remember, we're talking about the progeny, so we're looking for n2. n2 at any time t is equal to the decay constant of the parent divided by the decay constant of the progeny minus the decay constant of the parent. This describes the relative growth and decay. So the decay of the parent is growing into the progeny, but as the progeny decays, it's disappearing. So you have the parent decay rate filling the progeny, and then the progeny decay rate having the progeny disappear. The initial amount of the parent times e to the minus lambda 1 times t minus e to the minus lambda 2 times t plus any amount of the progeny that is originally present. So let's consider that term also. So now we have this relationship where we can use to provide an understanding of how much progeny is present at a given time t based upon an initial amount of parent and even an initial amount of progeny. So we have part of the equation which describes the growth of the progeny from the parent and then initial amount of progeny. So pretty straightforward. We have these two components that provide information related to the amount of the progeny available at any given time. Now, since we found n, the number of atoms, we can solve this equation for determining the activity of the progeny at any time by using the relationship between the number of atoms and activity. So activity equals lambda n. So we multiply this by lambda 2, so we take the term. Again, we have an initial amount of the parent, and now we have the progeny term. We can use this to find maximum progeny activity based upon just change of the progeny with respect to time equal to 0. We're maximizing, and let's solve for t. We have the equation where the time that it takes to reach this maximum is equal to the natural log of the ratio of the decay constants divided by the difference of the decay constants. And that's not too surprising. We don't need to understand the amount of material that's available, parent or progeny, for it to reach a maximum amount of progeny. All it is a ratio and a difference of the decay constants of the parent and the progeny. We can use this equation, input data that says if I have a generator, for instance, I'm making technetium-99m, which is a 6-hour half-life from the decay of molybdenum-99, so this is the parent, this is the progeny. Find the time for the maximum progeny activity. Well, we just plug in the lambda 2, which is the technetium. Lambda 1 is the molybdenum. We make sure the units are the same, days and hours. So make sure you convert this hours into days. And this basically says in about a day, this has reached a maximum. And this is actually a useful consideration, useful term. Technetium 99M is a workhorse for radiopharmaceuticals. It's sent to medical centers as molybdenum 99 on a generator. That generator, the molybdenum decays into technetium 99M. Molybdenum is decaying with a 2.75 day half-life. Technetium is a half-life of 6 hours. So this basically says you can separate the technetium from the molybdenum, wait another day, and you'll have reached a maximum amount of technetium you're going to get from that generator. In the previous slide, we used a differential to evaluate conditions where maximum amount of progeny would be created from the decay of a parent. We can actually make some more simple relationships based upon the relative differences between the decay constant of the parent and the decay constant of the progeny, or the half-life relationships. So in other words, there are relationships where if the half-life of the parent is much longer than the half-life of the progeny, you can simplify some of the equations. So let's take a few conditions. For instance, the simplest one would be that there's no progeny decay. The number of progeny atoms is just due to the decay of the parent. Number of progeny atoms keep growing, and the parent value keeps decreasing. So this is where if I had an isotope that was decaying directly into a stable progeny, that would be the case. And let's say if the progeny is radioactive. There's a few different cases where there's no equilibrium. Equilibrium means that eventually relationship between the decay of the parent and the decay of the progeny be established. If the parent is shorter lived than the progeny, or if the decay constant of the parent is much larger than the progeny, no equilibrium is attained. Progeny obtains a maximum activity when this condition is solved. But imagine you have a condition where the parent has a half-life of a second and the progeny has a half-life of a year. So within 10 seconds, all the parents decay and all those atoms are now progeny atoms where its half-life is a year. So within a year, half those progeny atoms will have decayed. So initially, you'll get this burst of parent activity, then decay will be solely based upon the decay of the progeny. Another relationship is where the parent half-life is greater than the progeny half-life. And we'll see that there's actually two types of relationships that we can describe this way. One is transient equilibrium. In this case, where the parent half-life is about 10 times that of the progeny half-life. One of the other properties is that due to the relatively short parent half-life, the activity of the parent may change during the measurement time. So this is called transient equilibrium, so that there's a change that's ongoing. Now the decay constant of the progeny is going to be greater than the decay constant of the parent. The ratio between the parent progeny becomes constant over time. As we see, as shown here, here's the total activity. There's a activity of the parent. There's a progeny activity that grows in. That ratio becomes constant over time. Now, this ratio is going to be the same. The total value will change. So we see that this ratio is going to be constant. And as t goes to infinity, the activity goes towards 0. And we can collapse the equation so that the number of progeny atoms is approximately equal to the decay constant of the parent divided by the difference between the decay constant of the progeny and the decay constant of the parent times the initial amount of the parent, e to the minus lambda t, so the decay rate of the parent. It becomes this equation. And then we can just look at a ratio. The ratio between the number of progeny atoms and the number of parent atoms at equilibrium is equal to a ratio of the parent decay constant divided by the difference between the progeny and the parent decay constant. Now, imagine we have a condition where the parent is much, much longer lived than the progeny. Generally, what this means is that over an observed time frame, the parent activity doesn't change. So imagine you're measuring something that has a half-life of 1,000 years, 10,000 years, and you're measuring it for 100 hours. The amount of change that is going to occur in that parent will not be observable, but the progeny may grow in during the measurement time. So you may have an amount of parent, B shown here. The progeny grows in, and then the total activity is basically twice the parent activity. So in this case, the parent does not measurably decrease in many progeny half-lives. We see that that seems to be the case. And then we have this relationship from the transient equilibrium. And lambda 2 minus lambda 1. Lambda 1 is a very small number. It's fundamentally just equal to lambda 2. So we get these relationships where n, the number of progeny atoms, divided by the number of parent atoms, is just equal to a ratio of the decay constants. And we actually see that what we get over time is that the activities of the two become constant. If I were to take this equation, n1 lambda 1 is equal to n2 lambda 2. So this equation, our transient equilibrium, since this value is small, we basically eliminate it from the equation for the secular equilibrium. And then we get these conditions, and the key condition being that the activity of the progeny winds up being equal to the activity of the parent. Well, what if we have a condition of many decays? So parent, one progeny to the next, to the next. So here's an example of a decay chain that you could calculate with the Bateman equation. It's the decay of neptunium-237 going all the way to bismuth-209, and then they even show the decay of bismuth-209 to the thallium-205. As a note, this is somewhat controversial since most data sources show bismuth-209 as a stable isotope. Let's take the example of the second progeny, which would be indicated by N3, since N1 is the parent, N2 is the first progeny, N3 would be the second progeny, and so forth. So that's the change in the specified progeny with respect to time is just equal to the decay of the progeny 1 that is populating progeny 2 minus the decay of progeny 2. And we use the Bateman solution to calculate this entire chain. And the equation for the Bateman solution is shown here. It assumes that only parent is present at time 0, and we have a factor where this C1, C2, Cn factor, so whatever n is, the number of progeny to be calculated, it's equal to this factor here, which is shown as the decay constants from 1 to n minus 1, and the difference between the decay constants of 2 minus 1, of 3 minus 1, so of all of them for this subscript value, all the decay constants minus that value, time the initial amount of the parent. This C2 value, and again we've got C2 e to the minus lambda 2, so that's the progeny 1 decay constant. Well, that's just equal to, again, the same factors here, all the decay constants to n minus 1. So depending upon what your n value is here. And then the decay constant of 1 minus 2, decay constant of 3 minus 2. Now we've taken what we're subtracting the decay constant by is the coefficient or the factor of this C value. It goes on and on. So you can build many, many chains. As you can imagine, writing this yourself, there's a lot to take into account. Another way to do this is to get a Bateman solver. There's Bateman solvers available. One of these programs that solves isotope growth and decay will be presented and can be found at this website. And if we go to this website, you'll see a page. Click here to download the program. It'll ask you for some information, and then you can download the program. This version, there's also a link on the Canvas site. version 2002 available. You can read the information that's available. They are looking for feedback, so they'd be happy to have feedback. And this is a PC program, so it does not run on an Apple product. We'll use the other ERG program, version 2.002, which is copyright from 2012, to provide an example of just the decay of atoms as opposed to activity. So let's pick an isotope to start with. Let's select zirconium-95. So we select the element, then we select the isotope, zirconium-95, niobium-95, molybdenum-95, beta, 2 betas, and a stable molybdenum-95. The input data isn't done by clicking on this bar. It's done through the table. So let's just say there's 100 atoms of zirconium, fundamentally a percentage. And let's also include the molybdenum into the output since we're talking about atoms. Let's click on the parameters, pull up the parameters. Let's go for 200 days, shown here. The half-life is 64 days, 34 days, and stable. So we should see some growth and decay in this period. Select that. Let's calculate it. Here comes the graph. And sure enough, we see that zirconium decays, the niobium reaches a maximum, then starts to decay, and the molybdenum does nothing but increase since it's stable. We can select this bar. If I move this around, I get the day and the amount of the zirconium, niobium, molybdenum. I can see that the niobium, I can see where it kind of reaches a maximum, then where it starts going down, and I can quantify that. Just like the other program, I can evaluate the data. So here's an example of the amount of atoms as a function of time. Obviously, this value should be 0, but we go through and we can see that zirconium does nothing but decrease. Molybdenum goes up, reaches a maximum, then starts decreasing, and molybdenum just increases. It does not decay. And just like the other program, we can export the data. I can export it as a CSV file. There's also some data libraries. I can look at the emissions, the alpha. I can select an isotope alpha, beta, and the gamma emissions for the isotope. I can select niobium-95, look at its emissions, no alphas, 3 beta energies, 3 gamma energies. I get the energies and the decay probabilities. I can also look up atom, if I just have a gamma decay, I can write in, for instance, a gamma decay, 661.6 keV. I can do a tolerance of 0.1 keV, so it'll be 661.5 to 661.7. It pulls up all these values. So if I was interested in, if I just saw a gamma line, for instance, cesium-137, that's the gamma that I'm thinking of, I can get that gamma and also its decay probability. So this program, you could use this program, you can use the ERG 1.001. Either will work for looking at growth and decay, series, daughters, decay chains. You can get data out of both. If there's any assignments, these will be used on, they'll operate on PCs, they won't operate on Macintosh. And if you have an issue with that, we can resolve that through the course. One of the terms we discussed in the example of the uranium-238 decay is branching decay. And this showed a condition where an isotope will decay by 2 different routes. Alpha and beta was the example that was shown in that decay. Now, if you look up an isotope on the chart of the nuclides, you're only going to find one half-life. So an isotope only has one half-life, therefore it only has one decay constant. But actually what that decay constant is, it's fundamentally a sum of all the decay constants. However, often only one decay constant dominates. It's fundamentally equal to the observed decay constant. So that half-life is the observed half-life. If something has a very low probability, it has a large half-life, and it often isn't observed or difficult to observe. So for a branching ratio, you could actually calculate partial half-lives or partial decay constants. From this equation here, the sum of any decay constant is just equal to the sum of its components. And let's take an example of an isotope that decays by alpha and beta. So the alpha decay constant and the beta decay constant is equal to the total constant. The branching ratio is just the ratio of the decay constant of the alpha divided by the total decay constant. You could also look at the half-lives, where the branching ratio is the total half-life divided by the half-life of the decay route. So in this case, you'll observe that since it's a number less than 1, the half-life of the decay routes are less than the half-life that is provided in the observed half-life that's provided in the chart of the nuclides. So let's consider an example, bismuth 212. What's the half-life for each decay mode that decays by alpha and beta? We see that there's a 36% alpha branch, 64% beta branch. The decay constant's the half-life's about a minute. So log 2 divided by 60.55. The decay constant's about an hour. The half-life's about an hour. The decay constant is log 2 divided by 60.55 minutes. We see that the branching ratio is equal to, for the alpha, 0.36 is equal to the alpha decay constant divided by the total decay constant. Let's solve for the alpha decay constant. As shown here, we get a decay constant of 0.0041 inverse minutes. Log 2 divided by the half-life is equal to the decay constant. We use that to calculate the alpha decay, which is about 170 minutes. The alpha decay half-life. We do the same thing for the beta decay. We see that its value is about 95 minutes. We could calculate the half-life directly using this ratio. If I know that the half-life total is 60 minutes, the alpha half-life is equal to the total half-life divided by the branching ratio. Same thing for the beta, total half-life divided by the branching ratio. So in this way, if you're given a total half-life and a partial decay constant or partial half-life, you could calculate the branching ratio, or you can calculate the decay constants and the half-lives from the branching ratio. Here's an example of the utility of the equations we've just explored. This figure shows the radiotoxicity of radioactive waste as a function of time, and you see the radiotoxicity is listed in sieverts per metric ton of natural uranium. It's a way of comparing the toxicity of spent fuel to that of natural uranium. So there's this line that shows natural uranium ore. So the idea is, how long would you need to wait so that spent fuel becomes as toxic as natural uranium? And you see this point over here. Now the dose, and when we learn about dose, we're going to see that it's related to activity. So all the equations, the growth and decay equations we discussed, can be applied to generating this figure. And we see that we're able to break the waste into different components. There's fission products, which are generally short-lived, and that dose decreases over time. There's minor actinides and decay products. There's plutonium and decay products. So this gives you an idea of what components of radioactive waste contribute to the dose. And this is important when we discuss separations in radioactive waste treatment and the nuclear fuel cycle. We also see here that this is for an average burnup of 50 gigawatt days per metric ton for a light water reactor. And those are conditions of a nuclear reactor that we will briefly touch upon in this course, and we may have a full lecture in it. So overall, the equations we discussed can derive data such as this, over a period of 1,000,000 years, and in this case, the equations can be used to evaluate the radionuclide activity and dose over time. This concludes Lecture 3, Part 2 of Radioactive Decay Kinetics. When you've completed this lecture, please continue on to Part 3.